Hi, my name is Max Hawkins, and this spring I worked under Tim Bessard helping to develop Metal.jl, a GPU backend for Apple hardware. At its core, it's a GPU programming framework for macOS, primarily targeted to the M-series chipset. At its lowest level, it uses an Objective-C API from Apple that's not completely open source, so it did require some reverse engineering, and in the future will require even more. It also uses a custom LLVM version with a metal target to emit Apple-compliant LLVM modules for further compilation. It also leverages reusable GPU infrastructure from the Julia programming language, so primarily that's GPU arrays and GPU compiler, so that when we were creating Metal.jl, we did not have to write lots of redundant code between Metal.jl and CUDA or OneAPI, etc. On the right, you can see what the typical experience would be to get it set up. It's a simple add and using for most users. After that, away you go. But what can you do? If you're looking for a high-level array abstraction, that's provided via Metal Array. This is similar to cuArray, where high-level array abstractions can be dispatched directly to the GPU. So that's things like broadcast, reduce, sum, transpose, or nearly every CPU array operation you would think of or want to operate on can in some form be dispatched to the GPU. There may be some performance issues or bugs, but we are working, like any other developer, to improve the experience. If you're looking for kernel programming or lower level direct access, that is also exposed in Metal.jl. So on the left, you can see what a simple vector addition looks like. It's very similar to most of the other frameworks. You have to pre-allocate arrays, you have to define the kernel, and then the kernel is launched or compiled and launched via this @metal macro, which is similar to @CUDA or @OneAPI. Let's compare that to what it takes to do the same thing but in Metal shading language. If you just look at the kernel itself, they're very similar, although the indexing intrinsic is found in the arguments in MSL. But what you don't see are the 150 or so lines of setup code needed to manage all of the encoders, buffers, pipeline states, etc. Everything to get it working that with Metal.jl is hidden for the developer behind the scenes so that they can better focus on the programming task at hand. And I think this is super compelling. But if something is not meeting your performance expectations or is doing something rather odd, Metal.jl offers direct profiling. So unlike CUDA.jl, which requires you run the Julia session under NSYS or NCU, Julia offers it directly. So this macro will output a direct GPU report that can then be viewed by Xcode. So for viewing it, it does require Xcode install, which is non-trivial, but we're still working to develop the interface and reduce the dependencies here. If everything's all working, you can see what data you have at your fingertips. So this is kind of similar to NSYS in that you can see the GPU counters, specific like kernel, occupancy, and other metrics, or you can see high-level diagrams like dependency graphs or all the resources that were being used for this particular session. And so I think this can be very powerful in the right hands. As for code introspection, it's very similar to the other GPU frameworks. The one thing that's specific to Metal.jl is this @device_code metal macro. This will show the Apple IR compliant LLVM module that we had to make to integrate with Apple's low-level compiler. This is different from the traditional Julia LLVM module. Primarily, there are many things, but primarily the argument metadata associated with it. And so you can see for just a simple broadcast across a 3-element array or a 5-element array here, it emits a lot of metadata. This is just a subset of what's emitted. So there are lots of things about the indexing intrinsics and the buffers, etc. So if you need to introspect this code or debug something, there are tools available for you. But there also are some requirements. Some of them are hard, some of them are soft. First, you need a Mac device. That's a given. And you probably will want an M-series chip device with that. But if you have an older Mac with an AMD GPU or other non-Apple GPU, this will probably still work most of the time, but there might be some corner cases that aren't caught. So just be aware of that. One hard requirement is Julia 1.8, as Metal.jl is dependent on LLVM 13+. So work has already been done to get this working in Julia 1.9 with LLVM 14, so no need to worry about that. But if you're trying to use Julia 1.7 with Metal.jl, that's not going to work, at least currently. macOS 13 is also a soft requirement, as the package will work with older versions of macOS, but with Ventura, Apple brought out Metal 3.0, which is a huge announcement, primarily because it brought bindless arguments, which previously you had to encode every specific argument that was passed to the kernels. And so for arbitrarily deep structures that may be dealt with differently from Julia's side versus Apple's side, that quickly got tricky and was what I spent a large part of my internship and what Tim spent a few weeks working on, only for Apple to come out a few days later and say, we're deprecating the entire API. So that was a bittersweet thing, but moving forward, you're probably going to want Metal 3.0. Metal.jl has a few unique aspects. Chief among them is the unified memory architecture, meaning that the GPU, CPU, and other hardware accelerators on the M-series chips all have the same memory module. They pull from the same memory pool. So there's no need to synchronize memory across a PCIe lane like is common in CUDA or AMD land. This allows for some amazing things to happen in the future, but because it's of this unique potential, we want to make sure that we get the API right, so it's still under development. At right, you can see what that looks like right now, but it's somewhat ugly and clunky. Another unique thing is that there's more than just a GPU on the M-series chip. So it contains a CPU, it contains a neural engine, vectorized instructions that are available to it as well. There's also this reusable assembler and disassembler tool for Metal libraries that came out of the Metal.jl development. And so that enables other people to not have to redundantly redo the work that Tim did. There's also some idiosyncrasies with the indexing intrinsics in Metal.jl, but for that I'll just refer you to the documentation. It's straightforward. As for future work, like most other packages, we just want to improve performance, add functionality, reduce dependencies, and incorporate into the larger Julia ecosystem. So for Metal.jl, that means things like kernel abstractions or gem kernels. And so if you or anyone you know wants to help out and contribute to this community, please do reach out. Here is the link to the code base. And I just want to take the last few seconds to thank Tim Bassard and Valentin Cherevi for their amazing mentorship and help with this, as well as thank the rest of the people that contributed to this package and helped us along the way. Thank you.